Question number 4. Civil engineers are designing a floating platform to be used at sea, figure 4.1. Shows a model for one section of this platform, a sealed metal tube of uniform cross-sectional area loaded with small pieces of lead, floating upright in equilibrium in water. So this looks to be the sort of Archimedes principle, where the weight of the water being displaced equals the weight of the object floating in it. The tube has a length of 300 millimeters, so I better indicate that on the picture. I'll call that length capital L, 300 millimeters, and a diameter of 50 millimeters, so that would make the radius of this area, cross-sectional area, the radius would be 25 millimeters. The total mass of the lead tube is 0.5 kilogram. Show that the length of the tube above the surface, so that L there, is more than 40 millimeters. So the question is saying little l equals question mark, basically, and the answer should be a little bit more than 40 millimeters. And the density of water is 1,000 kilograms per meter cubed. So what I need to do is to say that the weight of the water being displaced is equal to the weight of the tube. So I need the length of the tube of water for my calculations. So this length I'm going to call capital L subtract little l. And if I start with the density equation, density equals mass divided by volume. It's the volume of a cylinder, so that's going to be mass divided by length times area. The area is that of a circle, so that's going to be mass divided by length times pi times r squared. And then rearrange to make n the subject, I end up with density times area times length. But what I want is to say that the mass of the metal tube is also equal to the mass of the water being displaced, and that would be the density of water times the cross-sectional area times the length of the water pipe, so the length of that water cylinder there. So this can be the mass, 0.5 kilograms, and then this bit could be the water cylinder, this part of the picture here, so this water cylinder here. So if I take this equation now and rearrange it to make little l the subject, I end up with little l equals capital L minus mass divided by density times area. And now all I need to do is put in the numbers. Capital L, the length of the metal pipe, is 0.3, subtract the mass of the water being displaced, which is the same as the mass of the pipe, 0.50 kilograms, divided by the density of water, 1000 times pi r squared times pi times, so 25 millimeters in meters, 0.025 squared. All I need to do is plug that in on a calculator, and I end up with 0.04535, which rounds to two sig figs, 0.045. This would be the length in meters, and to convert that into millimeters, that would be 45 millimeters, which is the answer that I'm looking for, because the question asks for show that the length L of the tube above the surface is more than 40 millimeters, and 45 millimeters matches that. Part B, when the tube is pushed down a small amount into the water and released, it moves vertically up and down with simple harmonic motion. The period of these oscillations which quickly die away is about 1 second. The oscillations of the tube can be maintained over a range of low frequencies by using a flexible link to a simple harmonic oscillator. So the simple harmonic oscillator is going to be the driving oscillator, and the tube in the water is going to be the slave oscillator. Figure 4.2, the graph, shows a graph of amplitude of vertical oscillations of the tube against frequency obtained from this experiment. So what we can see is we've got resonance here. This frequency would be the natural frequency of oscillation for the tube in the water. And then if we have a look down here, this would be the driving oscillator. So when the frequency is so low, literally the tube will oscillate with whatever amplitude and frequency the driving oscillator is moving at. So let's have a look. Use this information in figure 4.2 to state the amplitude of the motion of the oscillator, not the tube, the driving oscillator. So that's going to be read directly from the graph right here, and that's going to be 5, double check the units, 5 millimeters. So as I'm reading off a graph, I'm not going to put 5.0 because all I've got is little squares, 5 little squares, 5. Add a suitable scale to the frequency axes, figure 4.2. I think up here I did spot a clue. The period of these oscillations, which quickly die away, is about 1 second, and frequency is 1 over time period, and 1 divided by 1 is 1. So this point where the oscillations start to die away is for 1 hertz as well. So I think the sensible scale, this would have to be 1. 1.0, this would have to be 0.5, so 0, 0.51, 1.5, 2.0, yada yada yada, dot 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 dot. The experiment is repeated in a much more viscous liquid, such as motor oil. On figure 4.2, sketch the graph that you would predict from this experiment. 2 things. I think the line would have to be starting at the 5, but it would have to be much lower than the line that's been drawn, and the natural frequency of oscillation in a more viscous fluid is going to be reduced, so I'd need to have my peak appearing a little bit to the left of the original peak, so I'll have it peaking around about there, and then keep the rest of it below the line like so. So that was question 4. All done.